Hello everyone. We continue our unit with alkanes and their reactions. So we have actually already gone over, just to review, alkanes, alkenes, alkynes at this point, so lessons 1 and 2. And we continue now with reactions of alkanes. There are three main kinds, or we will review or go over. So to begin, we know that alkanes have relatively strong sigma bonds. Now, again, that is a term that we have yet to completely define. More will come in our second unit. So for now, all we need to know is that alkanes are connected with sigma bonds rather with just covalent bonds. We'll get to the details later. Okay, and the three types of reactions that we're going to look at now is combustion, both complete and incomplete, and that should be reviewed from at least a couple of years ago. Also substitution, and in this case, halogenation. We'll look briefly at the mechanism involved there, and also look briefly at the last reaction, thermal cracking. Okay, so we begin with what you should already have some background knowledge in. So combustion essentially is when you have oxygen present, and that will of course require a catalyst or initial amount of energy for that reaction to take place. Common examples are anything derived from fossil fuels, such as octane, not the only compound, but a component of gasoline, propane, and maybe some barbecues, tanks, a butane-filled lighter. Those types of things will undergo a combustion reaction in the presence of oxygen with an initial amount of energy called activation energy, which is a topic for another unit. Okay, so complete combustion essentially means that there is a sufficient amount of oxygen for the combustion to take place so that you have carbon dioxide and water as your sole two products, right? So this is an alkane here, appears to be octane in the presence of oxygen, produces simply carbon dioxide and water, just the two of them. Also, a side note, these are one of the harder reactions to balance, but that isn't the focus in this unit, so that's a good thing. And an incomplete combustion reaction still requires oxygen. However, the idea behind this is that there is not enough oxygen for this to react in the previous manner. Instead, you get a couple of other products produced. So you get the normally present CO2 and water usually in the form of a vapor, and carbon monoxide, that's that dangerous one, and just solid carbon soot that is present in an incomplete combustion. Okay, so now on to something that is new. Substitution means that you're going to substitute a hydrogen with a halogen. So one halogen is going to replace a hydrogen present in your alkane, and this requires UV light or heat. So here's an example. Here we have methane. Let's get out a pen. Okay, so here we have methane, and the molecule looks like this. Right, in the presence of chlorine gas, your catalysts required are UV and heat. Now we'll briefly talk about the mechanism in the next slide, but you need one of these for this reaction to take place. And what's happening is a chlorine molecule is going to, or chlorine atom is going to bump out one of these hydrogens to create a halogenated version of this methane. Right? And then here is your byproduct from that removed hydrogen combining with the other chlorine atom. But here is the mechanism in some more detail. Okay, so it's important before I even show you this to mention that this reaction is not site specific. So that UV light that's required for the reaction to take place, but the reason it's there is because that UV light is going to hit that covalent, that relatively stable covalent bond, destabilizing it, moving electrons that wouldn't normally move, so that UV light will break apart these two electrons that form this covalent bond. And you can't tell UV light just to please only hit this one site. Instead, it can interact with any of these bonds, so it's non-site specific. That means you get a multiple number of possibilities in terms of product. The mechanism here would also involves what's called a free radical. Now, I said that UV light could hit the methane, molecule at any of these covalent bonds, it can also hit this chlorine atom. Right, it can hit that chlorine atom, bumping these bumping these electrons out, creating what's called a free radical. Very reactive, very unstable. That can then interact with methane and begin the substitution reaction like this. Right, so in the presence of the necessary UV light or heat, free radicals can be created, such as this chlorine free radical, right, that bumps out an atom, rather an electron in this carbon-hydrogen bond, right, creating a methyl free radical, right, also then creating a hydrogen chloride as a byproduct. So that hydrogen would bind with the other chlorine molecule here, and you would get that reaction. So this new methyl radical will instantly react with the in the presence of the chlorine radical as well. And here's that mechanism in a bit more detail. So you have this chlorine radical, right? That can lead to a methyl radical, right? Then this will react. Our chlorine is going to react with that bumped out hydrogen to produce hydrogen chloride. Okay, and continuing the reaction, creating another chlorine. Right, there's different ways, rather, making a carbon-chlorine bond. There are different ways to show this. Perhaps this isn't the best one. I'll draw one quickly for you right now, one that I might draw in class. Okay, so maybe let's make a new page here. Let's start here. Okay, we'll begin with a chlorine free radical. So, oh, I jumped ahead and I made chlorine. Okay, so this is methane. Okay, chlorine here. Right, so UV light comes in, it hits this, it creates a chlorine free radical. Okay, so this whole reaction takes place to begin the reaction, and here we have right. Now this can react, or this can interact with methane, bumping out one of the electrons that exist here. So in our next step of the reaction, it could look like this. Right. Then in the presence of this other chlorine, plus the hydrogen and that chlorine radical, right? The final step. We have an alkyl halide produced, a halogen attached to what used to be methane, and a byproduct of hydrogen chloride. And there you go. So that mechanism shown in another way here demonstrates how a substitution reaction occurs in an alkane. Okay, again, these aren't site specific, so we can think about what that means. You could have, let's just draw it out here. You could have a propane molecule, right? And at any of these hydrogens can be replaced with a chlorine. Oops. Right, so we could get this one replaced with the chlorine. It could just be over there, or we could have a chlorine here, or we could have chlorines everywhere, right? So we could have different chlorines placed, different amounts, different spots, substituting different hydrogens, right? So there could be a whole slew of different products produced in this substitution reaction, and to separate these, they might have slightly different boiling points, so we can use a fractional distillation. So what's happening here is your mixture of all these substances is placed inside here. It's heated carefully, measured with a thermometer at the top. So if you're looking for a specific compound, right, so let's say you only want one chlorine attached to this propane, that has a specific a specific boiling point. So you heat it up to that boiling point itself, getting rid of everything else that came before it. So if anything else boiled before that certain temperature, that can be boiled away, condensed away, and then you're just going to focus on that one substance you want. So you're going to pick out a mixture of different alkyl halides. You're going to pick out the one that you need based on its boiling point. So this is how it works. You heat it up, gets heated evenly through this tube here. Right, it begins to then go through this condensing tube where here you have water coming in one end, cold water coming in one end, and coming out the other end. Now this tube is a double layer tube. So on the inside you have that hot vapor, and on the outside, so on the inside tube you have the hot vapor, and on the outside is where you have water cooling it down so it condenses quickly into a flask where you can collect the specific compound you need. So that's how you can separate based on boiling points. I'm going to skip this because we do spend a lot of time on reactions of alkyl halides. Maybe just to show you how it looks like, you can have an alkyl halide in the presence of water. It gets substituted and forms an alcohol, right? But that's not the focus for today. Again, another picture showing you fractional distillation. All right, last reaction is thermal cracking. So another non-site specific reaction. Essentially what happens is you have a long hydrocarbon chain. So a long hydrocarbon chain, and in the presence of a catalyst and a tremendous amount of heat, you can then break certain parts of these chains. So maybe over here, and that would give you ethane. Maybe over there, and that gives you 1, 2, 3, 4, 5, 6, 7, well, 6, yep, 6, 7, heptane, right? So it gives you different lengths of hydrocarbon chains that were derived from a much larger one. That much larger one is referring to often crude oil. So different products can come from fossil fuels. Typically the reaction can involve aluminum oxide or silicon dioxide in the presence of a lot of heat. That's what this triangle with the H means. You can then get different products. Right, so here I've broken it up into two, but it can be a whole number of them. So in this 10 carbon long hydrocarbon chain, you can have octane and ethane produced, but it could have very well had hexane and octane, because of course there are many of these. They can be broken up into different size carbon chains. Again, just like that non-site specific halogenation, you can separate these products using distillation, right? So this can be refined away based on, or distilled based on their certain boiling points. So crude oil is pumped in here, reaction takes place in a furnace, and substances that evaporate at certain temperatures can be fractionated out. So here we have at 150 degrees Celsius, we might get a mixture of gas and petrol. So that can be removed at this column, at different points of this column. Kerosene, diesel oil at 300, fuel oil at 370, other larger molecules at 400 degrees Celsius. So from oil, you get different products produced based on their boiling points. Okay, so there isn't really a general formula. I've given you one here, not a general one, but an example of one. Just know that at different points along a carbon chain, you can get different lengths of hydrocarbons produced after thermal cracking. And that's it. So by now, hopefully you have your textbooks. Otherwise, I will have some information posted for you about your practice work, but here's the practice work. Hope this helped. Be sure to post any questions on our team site and ask in class.